Hello, everybody. This is the next lecture, and this lecture will serve as a bridge from the Ztest stuff that we were doing in the last lecture, which I told you was sort of more conceptual in the sense that we really don't just have one sample. We typically have a more fuller experiment or study that we do statistics with, but that one sample Z served as a bridge from the conceptual stuff of the Z-scores to the real world of what we actually do in statistics for social sciences. And this is also a bridge in the sense that it's covering a topic about the first statistic that we're going to cover that's actually used in real research. Like I told you, the Z, the one sample Z, is typically not used in research because it's not set up to have two different groups that you collect data from. We just are doing things conceptually with the Z-scores on the normal curve. And so this is the first statistic that we're going to cover that's really applied and we use in the real world. This is going to be hopefully a relatively brief bridge to the statistic. We're going to sort of do the introduction of the statistic in this lecture. And then in the next lecture, we're going to actually start doing numbers. So I don't think we're going to calculate anything in this lecture. We're going to introduce a few concepts. And so I'll just sort of warn you that there's some new things coming up. And at first you might think, oh, I don't understand this. Just like everything, you're not going to understand it at first. Just let it seep in a little bit in this lecture. And then in the next lecture, we actually are going to use some data and do some calculations, and then it becomes a little bit more concrete. And oftentimes people understand it more after doing that. So again, this lecture is covering a few new topics that we're going to use throughout the rest of the semester. So don't worry if you don't get it right away. We aren't going to do any numbers or calculations in this lecture. We're going to do it in the next lecture. We're just introducing stuff, so introduction to T-test. So just to review, you already know the Z-scores. So we started off with the Z-score with the Z-score with the Z-score for a score was that score minus the mean, and then we talked about that difference, that distance of the score from the mean didn't make any sense unless we standardize it, and so we had to take the standard deviation. So we took the difference from the score from the mean, and then we divided it by the standard deviation to get our Z-scores. That was the first thing we did. And then we started saying, well, we're going to start thinking about inferential statistics, and in inferential statistics where we're taking the sample's data and making some conclusions about the population, those inferences, those conclusions are they're always probability statements. So we're 95% sure the effect that we saw in our sample will show up for the population, for example. So since we're dealing with the inferential statistics, we had to add sample size because we already know the dating metaphor. You go out on one date, you can't make a very good prediction about whether that person's a good partner. You go out on 10 dates, a little bit better, you have more information, 20 dates, better, or more time spent, just more pieces of information, the better your predictions. So the same thing for sample size. The larger your sample size, the more pieces of information you have to make your estimates on, the more likely you can say something with more certainty if you have a larger sample size. Larger sample size, more pieces of information to make a prediction about the population. You have more confidence with that larger sample size because you have more pieces of information that you're basing your estimates on. So you see that the formula above there, that's the one sample Z formula. So that was the sample mean minus the population mean divided by the standard deviation. But in this case, the standard deviation was corrected for by the sample size. So the standard deviation is divided by the square root of n. And the bigger that n got, so the more pieces of information you had, the smaller the denominator is, the bottom of that formula is, and therefore you have a larger Z and you're more likely to find something. more likely to find an effect that is there. And then we also did something with the one sample Z where we would use a placebo group or a control group to estimate the population mean. So they're the estimate of the population mean because you don't have the treatment for them. So the sample mean might be you give 6 drinks to somebody and see their attraction to other people. And then the placebo group is you give them fake alcohol and you see their attraction to people. And so that placebo group is an estimate of how people are just attracted to people in general. So it's an estimate of the population mean, that little U thing at the end there on top, the mu. And so the bottom part of the formula, we really didn't talk a lot about that, but that's the standard error. So if you remember way back with the central limit theorem, we talked about the standard error of the mean. Well, that's basically what that is. And so the standard error of the mean on the bottom there, and it's using population abbreviations or symbols, is the standard deviation divided by the square root of n. So the bottom part of that one sample Z formula is called standard error. And again, standard error is just the standard deviation adjusted for by the sample size, the square root of n. And we already know that, again, the more pieces of information you have, the larger your n, the smaller the standard of error. You have more pieces of information, your predictions are better, you're going to make less errors. So that's what we've done so far. So we're going to get away from the Z-scores, but it's not going to be a far distance away. It's going to be what we're going to be doing in this lecture is very close to what we've been doing so far. Z-scores really are not practical because really we're supposed to have the population mean, and we rarely have the population mean. We were just, in the last lecture, estimating it with a placebo or control group that doesn't get the treatment. But usually we don't know the population mean. And so we don't know the population mean, we don't know the population standard deviation. We only have the sample data, obviously. And then also the other problem with the Z-scores is that it's in a sort of an unreal world of perfect normal distributions. So remember that the Z-table that we're using is for a perfect normal distribution. It could have different kurtosis. It doesn't matter about kurtosis. So the kurtosis could change. So the shape of the standard normal distribution might change, but it's really about perfect normal distributions. And we know that we typically don't have that with our samples data. So again, don't worry, the Z-scores are very useful as transition things in what we're studying, but we have to move away from them now. But we're using them as a bridge to go to what's called a T-test because Z-scores don't really apply because of these things that we just covered in this slide. And so the T-statistic, so the T-test is really a real-world version of the Z-score. And we'll see that the T-test formula is very close to the Z-score formula. And basically, the T-test is for the real world where we have normal distributions, but they're not perfect. So they're basically, they look normal and they are basically normal distributions, but they're not perfectly normal. So we can't really use those Z-scores. We have to adjust our estimates based on the fact that our samples data is going to be slightly off. It's not going to be a perfect normal distribution, but it might be roughly normal. And also we're going to be using actual data from our sample. So there's no assumptions that we know population values of the mean or standard deviation. We're going to use actual numbers that we can calculate from our actual data from our sample. And so here's the T-test. So it's actually the same as the Z, even though they write it a little bit different here. But basically, the T-test is the same thing as the Z. Remember, we have the population mean. That little m is the same thing as the x bar. The x with a line on top of it, it's the mean, it's the sample mean. So sample mean minus the population mean over the standard error of the mean. So that little sm is the standard error of the mean. What is that again? The standard error of the mean is on the lower right-hand side. It's the standard deviation divided by the square root of n. So the T-statistic mathematically is exactly the same as that for the Z-test. So we're really talking about the same thing. And I want to sort of draw us out a little bit broader So remember, the top is the difference between two things, and we've been doing that all along. So we had the initial z that we did, and it was the difference between somebody's score and the mean. And we didn't know exactly how far it was from the mean unless we standardized it by dividing the standard dividing that by the standard deviation. So it's the difference between two things, the score, a person's score, and the mean, but we have to standardize it to make sense about exactly how far it really is from the mean, because points don't matter, but standard deviations matter. And then we had the one sample z, which was the difference between two things on top, the difference between the sample mean and the population mean, but we don't know how big that difference is unless we compare it to something. Something we compared to was the standard error. So the standard error is just the standard deviation divided by the square root of n. And I think I'm going to start drawing this because I want people to see that this is really all the same stuff. So we had just the z-score, and the z-score was just simply somebody's score minus the mean. So how far is it from the mean? So the difference between two things on top. Well, we don't know how big that difference is, how far somebody is from the mean. We really don't know. Points don't really matter. What matters is standard deviation units. So we can only judge the top, how far you are from the mean, if we can standardize it by dividing it by the standard deviation units to see how far you are on the normal curve, what percentile you're at. Then we had the one sample. Sorry about that, just one sample. So one sample z. The only difference there was, and again, we're looking at the difference between two things. So the difference between two things here, and this is just basically a sample mean, which is usually a treatment group, and then the population value, which is usually we can have a placebo or a control group. And then the difference between these two means, we're not sure if they're really different unless we can compare them to something. And the thing that we compare it to is the standard error. And the standard error is just the same thing as before. We want the standard deviation, but since we're doing inferential statistics, we care about how many pieces of information we have. So we're adding the sample size here, because we're starting to think about inferential statistics where we're making probability statements about how likely our sample's findings applies to the population. And so we need to have some sort of probability statements, but the more pieces of information we have to base our estimates on from our sample, the more confidence we have in inferring something from our sample to our population. So we care now about sample size and number of pieces of information that we're making our estimates from. So this stuff is basically the same. It's the difference between two things. Well, we don't know how big of a difference it is between somebody's score and the mean, so we standardize it with the standard deviation. Same thing for this, same logic. Difference between two things, the difference between a treatment group, the sample mean, and the population mean without treatment. We don't know if there's a difference between those two groups. Essentially, we don't know if there's an effect of our IV unless we compare it to something. The something we compare it to is the standard error, which is, again, the standard deviation, but now we're starting to think about sample size also. And then this t-test that we just went over is this general t-test. We're going to go into specific formulas in a bit. Is the same thing. They put it as a sample mean versus the population mean, and again, it's the standard error, and the standard error is this. And again, they might use the little curlicue guy. That's just the standard deviation for the population. But really, what we're going to find is, we're going to talk about this later. So it's basically the same. It's the same formula. Well, not even basically. It's exactly the same formula. So it's the same question. First, we're going to look at, well, what's the difference between two things? And then, again, this is basically two groups. So the mean between two groups, is it different? So again, we could think about it, does our treatment have an effect? Did our treatment have an effect? Is there a difference between the treatment group and the placebo group? Well, we don't know whether that treatment is big or small unless we compare it to something. And the something we compare it to is the standard error. And the standard error is just simply, again, standard deviation divided by the square root of the sample size. So I just wanted to highlight this, that we were doing this way back when, a couple lectures ago, and then we did the one sample Z, but it's essentially the same thing as that. And now we're going to start doing t-test, and the t-test is essentially the same thing as the one sample Z. So while you might think, oh my gosh, now we have 3 formulas, you don't, you have 1 formula. So these things are connected. So again, we are now in the real world of sort of normal curves, but they're not perfect normal curves, so we can't use the Z table. So now we're going to use something called a t-test and a t-table. And we need to find that critical value for a t based on our sample size. I want to see if I have a table here. Yeah, I don't have a table here, so I'm going to actually draw this. So remember with the z's, the nice thing about the z's is that our critical value was always 1.645. Whether that was positive or negative is always 1.645 because the z table never changes. Every perfect normal curve is the same. That line is the same. But now it's different. So I'm going to draw this. I'm going to draw that one a little bit longer. So remember, we were using something like so this was a z. Our critical z was about 1.645. Not about, it was, exactly. And that didn't change for any of our one sample z-test. And again, this is where 5% of the scores lie on the z-table, which means if we get anything beyond this critical value of a z of 1.645, it's far enough from this mean in the middle to say it's different, to say that there's an effect. It's very unlikely to have, just by random chance, a score this high, way over here, a mean this high for a treatment group. So there's less than a 5% chance that we would say there's an effect for the treatment group, but really we're making a type 1 error. So we can live with a 5% chance. But with the t-test, we know that there's not a perfect normal curve and we have to adjust. And I think I'm going to erase this. I'm going to put it down below. Don't worry, I'm not going to get rid of it. That's a bit annoying. There we go. So this is the perfect world of the z-scores. Is this 1.645 was our critical value. So if you're not quite getting this, go back to the last lecture on one sample z. With a t-test, we aren't going to have perfect normal curves. So given that, we have to be a little bit more careful about what our critical values are. And what we're going to find is we're going to have to move in a bit. So we're going to have to move in a bit. So it's going to take. Oh, I'm sorry about this. I messed up there. So I'm going to erase this. We actually have to go out a bit. That's my mistake. So and the stuff I've said before is correct. I just need to redraw this. I'll make it big. So the 1.645 is right here. This is in the perfect world of the z-scores. So if we get a z that's more than 1.645, we say that it's far enough from the mean in the middle here to say that there's a difference between the placebo mean here and the treatment mean here. And again, it's 5% chance right here. But what happens is, in the world of t-test, the distribution is not a perfect normal curve, and so we have to be a little bit more cautious. And this is the mistake I made. I started going in. It's not in. You go out. So our critical values are farther away. So while the t-test, or I'm sorry, the z-test is just right here, we only have to go this far away, because in the real world with a t, we're going to have a distribution that's not perfectly normal. So we have to be more cautious. So you have to have a bigger t. I'm just going to make a number up. This is not necessarily what I've represented here, but it could be let's just say it might have to expand to 1.75. So now instead of having a number that's above 1.645, we now need a number above 1.75. I'm just making this up, but so we have to have a bigger number. You have to be farther away. Your treatment group, your alcohol group, has to be even farther away from the placebo group that didn't get any alcohol on attraction for the real world of a t-test than you do for a z. So in the t-test, we're moving farther away. So these are t's up here. But here's the thing, is it depends on the sample size. And I'm just talking conceptually here. So let's say that this is a sample size of 100. So we have quite a few pieces of information. Still not a perfect normal curve, but it's not too far away from the z line. And again, I'm just talking conceptually. These numbers are not exact numbers. Let's say that we only have 10 people. So if we only have 10 people in our sample, where do you think the line goes that we have to cross? Do you think it goes to the left, or do you think it goes to the right? Do you think it goes closer to the mean or farther away from the mean? I hope that you said farther away from the mean. This is, again, it's just conceptual. So if we have a sample size of just 10, so not only do we not have a perfect normal curve, and so we have to say we have to be a little bit more careful about our judgments versus a z, but now we have fewer pieces of information to make our estimates or our judgments on. So now we need even a bigger t. And I'm just going to make up something. Let's just say it's 2.5. I'm just making numbers up, but conceptually this is correct. So that's the logic of the t. For one, it's not a perfect normal curve, so we have to push the line farther that we have to cross to say there's a difference between our treatment group, alcohol, and our placebo group, no alcohol on attraction, just from the mere fact of not having a perfect normal curve. But then for the t's, the critical t, that line we have to cross, goes further and further out the smaller our sample size is. Again, what's the logic of that? Is you have fewer pieces of information to make your estimates. Therefore, your estimates are going to be a bit more off. You're going to make more errors. Your predictions are going to be a little bit more off. So we have to be even more cautious. We have to go even further from the mean to say something's going on in our sample, and it's probably going to apply to our population. So this is the t. And what we're going to do is we have a table that will give us these critical values. And we'll see in that table that the critical value of the t goes up if you have a smaller sample size, and the t goes down when you have larger sample size. But generally, you don't go as low as a z because this is the perfect world. Perfect world down here, real world down here, we have to adjust our line that we have to cross based on sample size, because that's the real world of research. So hopefully you kind of get this. Again, this is just a small taste of this stuff conceptually. We're just going to do this throughout the whole semester, essentially, this logic. And so let's go, and basically I already drew all this, so you can read this if you want to, but I drew it all for you. And remember, in our last lecture, we talked about this concept of degrees of freedom. So degrees of freedom is actually a way to say how many pieces of data, how many pieces of information did you make your estimates on. And it's very close to what a sample size is. It's just that you take the sample size n and you minus 1. Remember last lecture we talked about that? So let's say that we're in a physical class and there's 35 of you. If I know the scores, the exam scores for 34 people, and I know what the mean is for the class, I can actually tell you what that last person's score is. I don't even need to know everybody's individual score from the first 30, I'm sorry, there's 35 students, so the 34 students. So if I know the aggregate score, the sum score for 34 students in the class, and I know the mean for the test of the class, that last person, I know exactly what they got for their score. Because I can predict, I can know exactly that last person's score based on what the other 34 people got in the class. And so that's why it's called degrees of freedom. So 34 people's scores can vary. So I can know everybody's score as a sum and the mean, but I wouldn't know 34 people's scores. But if I know the sum of 34 people's scores and I know the mean for the class, I know what the 35th person's score is. So that's basically the logic. And what I'll say is this degrees of freedom is per sample. And this concept comes in good later, useful later. So each sample that you have, the degrees of freedom is n minus 1. And we'll talk more about degrees of freedom as we go further in the class, but just remember that's the concept. It's the number of pieces of information you're making your estimates from, and it's very close to what sample size is, n minus 1. And basically, the more degrees of freedom you have, the more pieces of information you're basing your estimates on, the more confidence you can say that your sample's data applies to the population. So that's the whole reason why we go over this stuff. Just shows you a difference between a normal distribution and a t-distribution. I'm okay if you don't really understand this, that's fine with me. It's just showing that the smaller your sample size, the more non-normal or non-perfectly normal your t-distribution is. So just think about t-distribution as real data. So the larger your sample, the closer you're going to get to a perfect normal curve. You might not be perfect, but you're going to get closer with a larger sample. Because everything kind of evens out when you have more people in your sample. It's going to look more perfectly normal. The fewer people in your sample, the more, or I should say the less perfectly normal your distribution will look like. It could look roughly normal, but it's still going to be some errors there. It's going to be less perfectly normal. This is what this is showing. The fewer people you have in your sample, the more you go away from a perfect normal curve. So here's a table we're going to be using. There is a table also in the textbook. I don't know exactly which appendix it is. You can look for the t-test or t-table, t-statistic table. You can use your textbook or you can use this one. And so we're going to use this one. I'm going to expand it so we can kind of see what the top looks like. Oops. Give me a second to fix this. This is a little bit annoying. Okay, there's the bar. So I want us just to look at this very much, very, very close. And this is my laptop. If I lean on it, it changes. So it says a t-test table. So one thing I want to highlight is we want to stick to this line. We are doing one tail test where we make predictions that one group is greater than another group. So we stick on this line that says one tail. So which column do we use? There's lots of columns here. So we use one tail. We want to stay here on one tail, and we're going to use the 0.05. So remember that we're always going to use an alpha of 0.05. And so we're going to use this column. Right here is the column we're going to be using. One tail, 0.05. That's the column we're going to be using. And then how do you find your critical value number? Well, you find it by going down to the degrees of freedom. So let's say I have a sample with a sample with 6 people. Degrees of freedom is 6 minus 1. So I go down to 5. See right here, there's 5. I can't highlight it for some reason. And then I just go on that row and I go all the way to this 0.05 on the top line, which is for one tail. That's our critical value. Our critical value for the t would be 2.015. We'd have to get a t from our calculations above that to say that there's an effect. So that's basically how it works. So again, I'm just introducing things to you. It will become clear when we actually do real problems with real data. So this is just introducing it. So you might want to save that table as a bookmark. And this is what we've already covered. This is a formula that we talked about. And basically all it's saying is that if the null hypothesis is true, our t is going to be a 0. that there's no difference between the two groups. At least the difference is not large enough compared to the standard error. So that's if the null hypothesis is correct. So the larger RT, the better in terms of possibly rejecting the null hypothesis. And we already know that. I already drew that, right? So we were saying that we have to cross that line to say that there's an effect, that critical value line that we drew on the curve. So basically, the larger your t, the more likely you're going to cross that line. The bigger the t, the more likely you're going to cross the line. And that's true for all of our statistics. For all of our statistics, the larger our statistic is, the more likely we're going to reject the HO. So assumptions of a t-test, and I think I went over this before, so I'm just going to do this real quickly. So it just says that the values, the scores, the data are independent. We talked about this in terms of method. So only our independent variable should be varying. There should be nothing else varying, affecting our dependent variable. If there's something else that is varying, that is affecting the dependent variable, then our statistics won't make any sense because we'll make wrong conclusions because we think only the alcohol is changing. And now only that is affecting the attraction ratings. But if something else is going on, let's say that our experimenter is acting different towards the two groups, if that is also varying, our statistic is not going to make the proper conclusion because there's something else going on making the observations not independent. So that's what independent means. There's nothing else affecting the scores except for the IV. And it says that, remember we talked about normality. Normality is something that's important in all of our inferential statistics, but with a t-test, it's pretty good. It's robust. Remember what I said about robust? Robust means even if we violate the assumption, in most cases, the statistic still is decent. And so even with a relatively small sample of 30, if we get about 30 in terms of a sample size, we don't really care much about whether it's normal or not. It's not going to have much effect on our conclusions. So while we say that there is an assumption of normality, it's pretty robust because if we get about 30 people in our sample, we don't really have to worry too much about that assumption. It doesn't affect our scores much. So another concept I want to cover that's new is effect size. And I'm trying to remember if I covered it in the last one. I think I did. We actually started talking about this. Yeah, we had Cohens D last time. So remember with the hypothesis, null hypothesis statistical testing, it's all about probability. Remember, we're just saying that we're 95% sure that our population's data applies to our sample's data applies to the population, that there's a reliable effect there. Whatever effect we saw, that, for example, alcohol increased the attraction ratings over no alcohol, if we do a null hypothesis test, all it's saying is that we're thinking it's a pretty reliable, stable finding that would apply to our population, and we're 95% sure it would. And so the problem with that, again, is that if we have a larger sample size, it's relatively easy to find a small difference be reliable. Because the more pieces of information, the larger our sample size, the more confidence we say, well, even if it's small, it's pretty reliable, it's still going to be there. So the effect size tries to correct for that. So the effect size is actually how big is it? Not is it reliable or what percent of times are we going to see this in our population? It's really about how big is it? And in general, it's about, does it have a real world impact? So when we're going to be doing our statistics, and we're going to do this in the next lecture, we're going to have actual data, we not only want to do our hypothesis test in terms of the null hypothesis, whether we reject it or fail to reject it in the probability statements, but we also want to have effect size measures. And we already talked about this in the last lecture. This formula should look very familiar on the bottom. We call it Cohens D, but it's the same thing as what we had with our Z. Our first Z that we did was the difference between two things. We don't know how big that difference is unless we standardize it with the standard deviation. So the difference between the two means, the sample mean and the population mean here, we don't know how big that difference is. We don't know if how big that difference is between the two groups are. unless we standardize it by dividing it by the standard deviation. So again, we're just sort of conceptually talking about this now. We will do this with real numbers, with real examples in the next lecture, but just know that Cohens D effect size is just about how big is the difference. And we can only tell how big a difference is by comparing to the standard deviation. But this is not going to test our null hypothesis. Null hypothesis tests always have to take into account your sample size. You can see in this formula, there's no sample size here. And then I think we talked about this last lecture also, is that we make judgments about how big this effect size is based on the numbers here in this table. So anything 0.2, actually I have to change one of the things I just realized in the lecture. I have to think about this, but basically around 0.2, the small effect kicks in. So 0.2 to roughly 0.49 is a small effect. And then 0.5 to 0.79 is a medium effect. And then anything that's 8.8 and above is a large effect. So we use those words: small effect, medium effect, large effect. And then we have just one more measure of an effect size for a t. So the t is what the statistic we're going to do. That thing is called R-square. And this is just telling us the percent of variance explained. And we'll talk about this in the next lecture. So if this doesn't click in right away, don't worry, we'll talk about it more. So basically, the formula is on the right-hand side. We're going to take our t, we're going to square it. We're also going to put that on the bottom. So we're going to have t squared plus degrees of freedom. This tells us the percent of variance in the dV that's directly linked to the IV. So let's just say that we run this for the study we talked about with the alcohol and attraction. Let's say we get an R-square of 0.20. What does that mean? That means that 20% of the variance, the differences in people's attraction score, was directly linked to alcohol. So again, 20% of the differences, the variance in people's attraction scores, was directly linked to the alcohol, having alcohol or no alcohol. So that's how we interpret this statistic. Again, this is the first time you see it. We're going to do real numbers. In the next lecture, it'll become clearer. And then there's another concept we want to cover really quickly, which is confidence intervals. This is a little bit confusing, perhaps, to think about right now. I'm going to introduce it like this, but we're going to do it with numbers in the next lecture. So again, this is just an introduction. It will become clear when we have real examples in the next lecture. Basically, all this is telling us is a confidence interval means that if we did the same study many, many, many times, and we have a confidence interval that, for example, is 95%, which matches well because that is what we use for the alpha of 0.05. Remember our alpha that we've been studying, 0.05? We'll accept a 5% chance of making a type 1 error, saying there's an effect when there really isn't one. So that's actually a 95% confidence interval. What that means is that if we ran our study, and there's fewer ones here, but if we literally ran our study 100 times with that same sample size, so let's say it's 20. So we ran the same study 100 times with sample sizes of 20. 95 out of the 100 confidence intervals from our sample would cross the real population. So this just basically means that we're making a good prediction of the population value from our sample size. So I'm going to stop talking about this because I'm realizing that this is really difficult conceptually, but we'll talk about it more. But basically, that's what it's saying. If we calculate a confidence interval for all of our samples, 95% of the confidence intervals will cross the true value of the population. So this is going to become clear when we have real data. So don't worry if you're not quite getting this. We will revisit this topic. Here's the formula. I'm going to talk more about this in the next lecture. So I'm not going to worry about this formula per se. I'm just going to highlight that it's just a reworking for the t. So remember the t formula is this, and all we're doing is we're just shifting it. So this little population estimate comes out here because the confidence interval is about population estimates. And then all of a sudden now we have the mean, and the mean's alone, right? Because we already took the population mean out, so there's only a sample mean, so that's the only one. Then the mean's left over. And it's plus or minus, it's an interval, and then we have a t from the table. We'll talk about this in the next lecture, and we multiply that by the standard error. So I'm just going to highlight that formula. It comes from the t formula, but again, I have no expectation that you understand this yet. You will not understand this probably until we get to the data in the next lecture. So this lecture is kind of a little bit weird. We're kind of introducing some topics, but they're not going to become really clear until we have data in the next lecture. And don't worry about this at the moment. Don't worry about this. Don't worry about that. Okay, so that's it for this lecture. So we just introduced a few concepts. And don't worry if you don't remember a lot of what we just talked about. That's fine. You can review it. But basically, just remember the t-test is the real-world application of the z. Remember, the z is about perfect normal curves. The t is about the real world where we don't have perfect normal curves. We have to adjust our critical value, the line we have to cross for our sample size. And one of the things that we also learned is that we aren't only just testing the null hypothesis in terms of how reliably we can say that our samples data applies to the population, but we also want to know just how big is the difference between our two groups. Is there a big effect from our IV or is there a small one? So that's the effect size. And the final thing is that we're actually going to be calculating a confidence interval in the next lecture, and that's going to become a lot clearer when we have real data. So hopefully this is relatively useful just to at least prime your brain with what we're going to be doing in the next lecture. So the next lecture, we're going to actually do real statistics, have real numbers, do real tests, calculate effect sizes, calculate confidence intervals, and then things will become clear in that lecture. So this is just a transition lecture. So I'll talk to you in a bit in the next lecture.